Okay, now now that we know that the work done by moving a charge along an equipotential line is 0, let's look at another way of writing work. So in general, we can always write the work done by the electric field on a moving charge as, remember, work is force through a distance, right? And it's a dot product. So we have F dot displacement. Okay. But we can write this in terms of magnitudes. So we have magnitude of F, displacement, cosine of the angle between the force vector and the displacement vector. All right. Well, if we have a charge in an electric field that feels a force, this is really Fe, the electric force. And we know that that is QE. And then we have delta X and we have cos theta. Okay. Now, we can actually say something pretty smart about the electric field in this region. Because we know that the work done is 0 if we move on a line of equipotential. Oops, line. So 0 is equal to QE delta X cos theta. All right. Now, the only way for this equation to be true, right, our charge by definition is not 0. Electric field is not, we're not saying that's 0. We're moving, our displacement is not necessarily 0. But the only way to make this equation equal to 0 is by saying this angle is 90 degrees. If the angle between E and your displacement is 90 degrees, then this equation is true. Okay? So what this means is that if you go back, let's draw that parallel plate again. Plus, plus, plus. Minus, minus, minus. Here were our lines of equal potential. Let me draw that better. Okay. Then our electric field has to, right, we're moving, our displacement we said was down this way. We're moving along an equipotential. So this is telling us the electric field has to be perpendicular to that, 90 degrees. It's got to be something like this. Okay. So what we can take away from this is that electric fields are always perpendicular to lines of equipotential. Okay. So let's see one more case of what this looks like. The parallel plate one is the easiest because the lines of equipotential are really simple, right? They're just straight lines. What if we had a point charge? Oops. Okay, so first we have to draw are lines of equal potential around a point charge. In order to figure out what that looks like, let's look at the equation for the electric potential around a point charge, KQ over R. If we look at the electric potential a distance r away from a charge, okay, we could look anywhere on a circle around that point charge, and everywhere on that circle you're going to have an equal potential. Okay, so our lines of equal potential, I'm going to erase this, form circles around our point charge. So they look something like this. Try to be careful here. And these should be perfect circles, but I can't draw. All right, those are equipotential lines. Now, we just mentioned that the electric field lines always are perpendicular to the electric potential lines, electric equal potential lines. So are they in this case? Well, let's see. We know that electric field lines for positive charges go outward radially. Okay? So we do something straight up, can go straight down, straight across. All right, if you drew this correctly, you will notice that at every equipotential line, the electric field is always going to be perpendicular. And we know that not only because I just told you with that little work equation, but also because we know that if you have a radial vector, like the electric field, anywhere on the surface of a sphere or a circle, it's going to be perpendicular to the normal to that surface. So even though these circles and these red circles are not spheres, you can remember back to Gauss's law when we looked at the normal vector and how it compared to the direction of the electric field. Okay. We can tie this in with lab real quick. When you looked at when you did this second equipotential surface that you drew, that you ultimately had a 3D plot in not MATLAB, but Excel, and you sort of saw, and this is going to be really impossible for me to draw on this, but I'll try. You had a sheet that sort of looked like this, and one side of the sheet went up like a hill, and one side of the sheet was depressed like this. Okay. So you basically, it's another representation of those equal potentials. You basically had lines of equal potential going up like this, and then you had lines of equal potential on this well, sort of. So you have a hill up here where there was the positive point charge, and then down here you have an indentation, we'll call it a sinkhole, where the negative charge was located. Okay, and that's exactly what you're seeing. Okay, last thing that I want to do, and we'll be done, is how to actually compute the electric field from the electric potential. Okay, let's again consider a charge moving in an electric field as shown below. So we're going to go again from some point A up to some point B, and our electric field, I don't know, maybe it looks like this. Okay. What we're going to do is look at a tiny displacement, tiny displacement of Q. Okay, and we're going to call that displacement dr. Okay, so we're going to zoom in at a little point here. This is where Q is, and we're going to look at a tiny little displacement dr. And we're going to compute the tiny amount of electric potential, the tiny potential difference due to that displacement. What is the tiny potential difference due to the displacement dr? Okay. In order to figure this out, I'm going to remind you of our equation for that related potential to electric field. We had VA minus VB is equal to integral E dot, what did we have? E dot dx, is that how we wrote it? Or is it, oh no, we wrote it as E dot dr from A to B. Okay. So we're going to do something similar. If we have a tiny little a tiny little change in electric potential, that should be equal to E dot dr. Okay. Now, be careful here because I've included a minus sign, because remember this term over here in this equation was minus delta V. Okay, so we're looking at that change in V, but it's a tiny little one. So we have a minus dV is equal to E dot dr. Now, if you wanted to integrate this equation, that would give you this exact equation that I just wrote out here that we already had. This isn't going to help us. Okay, so we have to look at this a little bit differently. So instead of integrating, let's define E and dr. Okay. I'm going to make just generic vectors. Okay, I'm going to say the electric field vector will have some x component, we'll call it EX I hat, some y component, EY j hat, and some z component, EZ k hat. And likewise, our dr, our tiny little displacement vector, will be made up of a tiny little displacement in the x direction, plus a tiny little displacement in the y direction, plus a tiny little displacement in the z direction. Okay, we're just doing the most general case that we could possibly have. Now we're going to throw these into our equation for dV. So let's go to the next page. We have minus dV is equal to, remember when you do a dot product, you multiply the like components and add everything. So we multiply the x components with the x, so we get EX dx. We add that with EY dy. We add that with EZ dz. Okay. All right, this is okay. We're going to hold on to this. And we're going to make a couple assumptions. What if motion of Q was strictly in the x direction? If this is true, if you're only moving in the x direction, your displacement in y is going to be equal to 0, and so is your displacement in z. So we've simplified our equation considerably. Now we just have minus dv is equal to ex dx. And if we rearrange this, we have ex is equal to minus dv dx. Okay. This is how we're going to compute the x component of our electric field. Just take the derivative of your electric potential, and that'll give you electric field. Okay, well that's nice, but what about the other two directions? Okay. Let's see what happens. What if motion was strictly in the y direction now? Okay, so in that case, dx is going to be equal to 0, and again, dz is equal to 0. And our equation from dv, we get minus dv is ey dy. And again, rearranging, solving for e, we get minus the derivative of our potential with respect to y. And if you repeat this for z, Ez is equal to minus the derivative of potential with respect to z. All right, this is how we're going to calculate our electric field from electric potential. Now, electric potential is a field, right? It's a value at every point in space. So sometimes it's going to be a function of three variables, right? Imagine temperature in your room. That is a function of three variables. There's an x position, a y position, and a z position for every point in your room. Okay? Same thing with electric potential. Okay? And taking the derivative of this electric potential gives you electric field. So if we are given V of x, y, and z, the electric field can be found using, the electric field vector is going to be minus the derivative of the potential with respect to x in the x direction, minus the derivative of the potential with respect to y in the j direction, minus the derivative of the potential with respect to z in the k direction. Okay. You do these derivatives individually and add in the unit vectors and you get your electric field. Just a little caveat to this. These derivatives are not really real derivatives. They're called partial derivatives. We're going to pretend that they are normal derivatives, but usually you write them with a script d instead of a normal d. But we're not going to worry about that. The derivatives work the exact same way. You just call them partial derivatives, and I'll explain why in a second. Let me do a quick example. Okay. So if you can compute one derivative, you can find the electric field. Now, let's do one example to wrap it up, and I think it is example number, let me see here. Example number 15. In example 15, it says the electric potential in a certain region is given by the function v of x, y, and z is equal to minus 3x squared y, z cubed. Okay. So if I gave you an x coordinate, a y coordinate, and a z coordinate, you could tell me the electric potential at any point in this region. And it asks for what are the x, y, and z components of the electric field in this region. So we're looking for Ex, Ey, and Ez. Okay, well, we know how to calculate these components. We just figured out that if we want to calculate Ex, this is just minus the derivative of v with respect to x. Now we do have to be a little careful because these are special derivatives. So let's just plug in what we know v to be. We have minus the derivative with respect to x of this function, minus 3x squared y z cubed. Now, when you have a partial derivative, it means that you're only taking a derivative with respect to one variable. Okay, in this case, it's x. Okay. All other variables are treated as constants. Okay, so we assume when we're taking the derivative with respect to x, y is a constant and z is a constant. Okay, and so is 3, obviously. And that's exactly what we assumed back here. We said, what if the motion's only in the x direction? Y is a constant, 0, and z is a constant, 0. Okay. So let's actually compute this derivative. We can pull out all of the constants. You have Ex is, the minus signs will cancel, and you just have a 3. The y and the z cubed can come out, and then you're taking the derivative with respect to x of x squared. That's it. And what do we get? 2x. So we have 6x y z cubed for the x component of the electric field. All right. You've just computed your first partial derivative. But again, we're just going to call it a derivative. You'll get to partial derivatives when you take Calc 3. Ey. Okay. To get the y component, it's just minus dv dy. Okay. So we have minus d dy of minus 3x squared yz cubed. Do the exact same thing. Take out everything that is a constant relative to y, which means we're going to take out that minus 3, make it cancel the minus signs, take out the x squared, and take out the z cubed. And then you're just taking the derivative of y with respect to y, which is just 1. Okay, so Ey is going to just be 3x squared z cubed. And finally, Ez is minus dv dz, minus dv dz, minus 3x squared yz cubed. Take out all of the constants, 3x squared y, and then take the derivative of z cubed with respect to z, and you just get 3z squared. So the z component is 3x squared y, 9x squared y z squared. Okay. So in theory, you could write a vector for the electric field, which is a function of x, y, and z. Okay. You could write it like this. 6xyz cubed I hat plus 3x squared x squared z cubed j hat plus 9x squared y z squared k hat. Okay, that equation gives you the electric field vector at every point in this region. If I gave you an x, y, and z coordinate, like maybe I say x equals 0.1, y equals 0.1, z equals 0.1 meter. Okay. You could plug them into this equation and get a numerical value for the electric field. Right? Just plug in 0.1 for x, 0.1 for z, 0.1 for y. You'll have an x component, a y component, and a z component. Then I could ask you things like, what's the magnitude of that vector at that point? And good stuff like that. All right. I think that'll do it for now. And you should be all set for the homework. Email me if you have any questions. Come to FSG if you have questions or you want to go over stuff for the exam on Tuesday, because just a reminder, we don't have class on Monday because of President's Day. Again, FSG, my last little plug, FSG is in Ira Allen Forum from 3 to 6 every Thursday. Okay. All right. Email me with any questions, and I will see you guys hopefully at FSG or next week for the exam. All right. Bye.